So I'm Micah Tillman. I am one of the instructors at Stanford Online High School. So if any of you guys are from OHS, hello. And if you're not from OHS, hello. I'm in Pennsylvania. My undergraduate degree is in computer science, which required a lot of math. And I enjoyed math, but I'm not good enough at math to do math. So I'm like a math fan as opposed to a mathematician. I enjoy watching mathematicians do their work, and I like it when they try to explain what it is that they're doing to me. So whenever Numberphile posts a new video on YouTube or 3 Blue 1 Brown or whatever, I'm all over that. But I am a recreational mathematician, and that led me to do my PhD in philosophy on a mathematician named Edmund Husserl. Husserl was a German guy in the turn of the 20th century who would get into arguments with Gottlob Frege. And this was the time in mathematics when they were getting really worried about the foundations of mathematics and trying to find a firm foundation for it. Frege was the one who came up with a system to base mathematics on logic. And then a young Bertrand Russell wrote him a letter saying that there was a paradox built into the very nature of his attempt to base math on logic and set theory, and it ruined poor Frege. But Frege got what was coming to him because Frege was always mean to the guy that I was doing my dissertation on, Edmund Husserl. So I feel justified by history. And specifically, I wrote my dissertation on Edmund Husserl's first 2 books, where he was in Germany at that point in time. You had to write your dissertation and then what they called a Habilitationsschrift, which was essentially a second dissertation that you had to write in order to get a full-time job in academia. In Germany, they had the greatest universities in the world in the 1800s. So he wrote his Habilitationsschrift on, it's called The Philosophy of Arithmetic. And he's trying at that point to figure out what are the foundations of mathematics. At this point in Germany, they're also getting really interested in psychology. And so he begins to suspect that perhaps we can understand where mathematics comes from and why it works if we can understand how human beings engage with mathematical questions and problems. And that's what made Frege angry. Frege said, you're trying to base mathematics, which is an eternal logical system that's objective, on psychology, which is the most subjective thing ever. And through their debate, Husserl came to realize over the 10-year period between his Habilitationsschrift and his first book that he was Frege maybe was onto something and needed to focus more on logic than he had before. So I got really fascinated by the experience of mathematics. What is it like to do mathematics? Why does it work? And I became a math tutor in grad school. And I was particularly interested in the question of why my students, my tutees, were so miserable with math when I was having such a great time with it. Like, why did I find algebra fun when they found it like the most miserable thing in the entire world? And I realized that it's because I experienced math problems not as problems, but as puzzles. And it all felt like a game to me. And from watching Numberphile, and have you guys ever watched Numberphile on YouTube? From watching those videos, lots of interviews with mathematicians. It's worth watching if you haven't watched it. Numberphile, Numberphil, so the love of numbers. It seems like that's what mathematicians do: is they play all day and party all night. And no, it's you rock and roll all night and party every day. That's how the song goes.
I'm just going to interrupt for a minute here because it looks like a lot of people have just come in. So just to everyone who's come in, welcome. Dr. Tillman is in the middle of his lecture. It'll be about 45 minutes to an hour of lecture, then some discussion of problems. So I'll let him continue. Sorry about that.
Yeah, I recognize some of those names. Hey, Ethan. So that was just background on why you have a PhD in philosophy talking to you about mathematics here. I think I'm in the grand scale of mathematical ability. I've got more mathematical ability than a normal person and much less than an actual mathematician. So I'm in this, I like to be a bridge. So being a math tutor was really nice for me. But I would find myself in my free time with Excel, Microsoft Excel, trying to find ways to find patterns in prime numbers. Like that's what I would do in my spare time. And then when I wasn't doing that, I was writing Java programs to see if I could find patterns in prime numbers using fractals. And it's one of those things where you know you're never going to actually find what you're looking for, but it's still fun because maybe you will find what you're looking for. But then again, you're not a mathematician, so you're not smart enough to find what you're looking for. But what if you did? You would occasionally hear stories about amateur mathematicians who find new ways to tile the plane and stuff like that. And you think, well, maybe one of these days I'm going to find a new fractal or a new pattern in prime numbers. Never had much success with that until recently, when suddenly, maybe I could be. There's a lot of people on 4chan though, so put them together collectively, and they could be smarter than me. So what I'm going to do now is I'm going to ask Quinn to play a video for you, which will introduce the topic of my talk today, and I'll be quiet for a moment. So this is something you can find on YouTube later if you find it absolutely fascinating.
So I am sharing that now. Let me find it. There we go. So to anyone who didn't understand my reference, amateur mathematicians have had success. For example, there was a 4chan user that solved some long outstanding problem a while ago, which if you look it up, you can probably find because it's a pretty unique instance. Okay. Let me see if I can get this to work. Let me press this button again, maybe then it'll work.
Number line. This is the number line. It's the second most boring line in mathematics. It shows you whether one number is larger or smaller than another, and you can even tell roughly how much larger or smaller. But there's more to life than relative size, as any integer will tell you. Each whole number also has a rich internal structure created by the mysterious primes. The unique set of primes that combine to make a given number is called its prime factorization. And the prime factorizations of all the numbers on the line follow a secret fractal pattern. So I say we give the number line one more job, to show us the fractal beauty hidden inside of prime factorizations. For example, imagine we ask the number line to show us how many 2's are in each prime factorization. It could do this by turning a particular amount at each number. And if it turns, it will cease to be a boring straight line and become an interesting curve. The prime factorizations of 2, 6, 10, and 14 all contain 1 2, so the number line would turn clockwise 1 click at those numbers. The prime factorization of 4, in contrast, contains 2 2's, so that requires a clockwise turn of 2 clicks. The prime factorization of 8 contains 3 2's, so that means a turn of 3 clicks. And 16's prime factorization has 4 2's, so that's a turn of 4 clicks. All the odd numbers, in contrast, have no 2's in their prime factorizations, so the number line won't turn at all when it gets to them. So the number of clicks that the number line turns will indicate the number of 2's in each number's prime factorization. But how many degrees are in a click? What kind of base angle are we talking about here? Well, we have 360 degrees available to us, so I say we give them all a try. We'll start by setting each click, each base angle to something very small, then gradually increase the angle, and watch how the overall shape of the number line changes. And while we're at it, let's color code each number according to the angle it is turned. That will make it even easier to tell which prime factorizations contain the same number of 2's. With those rules in mind, I fired up the Unity game engine, wrote some C# code, fiddled with shaders, and set my simulation in motion. 3 days later, the simulation was complete, and I had a 7-hour film of what happens to the number line if you ask it to signal the contents of each integer's prime factorization by curving. Early on, when the size of a click is still very small, you notice that the number line turns into a circle and then starts lashing out periodically. I've got a theory about why this happens, but have yet to confirm it. As you increase the base angle, you start to get hints of some intriguing patterns. When you get to an angle of 20 degrees, or pi over 9 radians, you get this. Another clear pattern emerges at 25.7 degrees, or pi over 7 radians. And another pattern shows up at 36 degrees, or pi over 5 radians. Take a look at what happens around 60 degrees, or pi over 3 radians. The most intriguing thing to me occurs as you approach 90 degrees, or pi over 2 radians. This is a version of the fractal called the Levy Dragon, or Levy C-curve. I have no idea what it's doing here, but I intend to find out. And then at 120 degrees, or 2 pi over 3 radians, Levy comes back, but this time as what appears to be the Levy diamond fractal. As the base angle approaches 180 degrees, another concentric rings pattern emerges, then folds and unfolds like a fan. From 180 degrees on, all the patterns in fractals repeat, but in reverse order, till we reach 360 degrees and we are back to where we started. a straight line. There are many, many more shapes and fascinating behaviors in the full simulation, which I will link in the description below, and which you can access by clicking the card above. And if you want to learn more about all of this, please visit micatillman.com/numberline or micatillman.com/fractal. You can find links to those pages in the description below as well. Thanks for letting me share this little project with you. It's an ongoing thing, and you should see what happens when you ask the number line to curve based on the number of 3s or 5s in the prime factorization series. I hope you all have a fractally prime day.
So the video itself is in 60 frames a second at 1080p or whatever, but the fact that we're having to play it through multiple layers of things means that a lot of that was pretty choppy. But that's the basic idea that I was interested in finding out, is whether or not you could use the patterns that show up when you take a line and bend it into a fractal, which is often the way in which fractals are constructed. And if there was any connection between that and the types of patterns that might show up if you were looking for patterns in prime numbers. I got first, there's a link in chat. If you guys want to use chat, if you mouse over the bottom of the window, little buttons will appear, and there's a chat button that you can click on and actually see what's going on in chat. There's a number file video on what's called the Ulam spiral. And there was a mathematician named Ulam who got bored in the middle of a lecture one day and decided to see what would happen if he wrote out all the numbers, all the integers, the positive integers, in a spiral pattern, and then circled all the primes. And it turned out that there were patterns in the distribution of the prime numbers in this spiral. 3 Blue, 1 Brown has a really great video on why that happens. It's nothing particularly interesting in the end, but it's enough to make people like me intrigued. And so this got me thinking about other ways you could do this, and it led me to a website called the Online Encyclopedia of Integer Sequences. Have any of you guys ever encountered the Online Encyclopedia of Integer Sequences? It feels like one of the most nerdy things in the world.
It's great to use when you're trying to find if your integer sequence matches things.
Yeah,
And
yeah.
Yes, I've actually used it numerous times for several things like that. That actually led me to solving the problem once.
Nice. I'm sure that what's-his-face, the guy Sloan, I think, is the person who started. I'm sure he would love to hear that. So I started searching around and found out that really what I was interested in are called the p-adic valuations of n. So if you were to go to the oeis.org and run a search for the letter P and then the word adic, A-D-I-C, you will get a number of results. And basically the idea is that you can think about each of the numbers, each of the positive integers along the number line, not in terms of its sequence of one after the other, but in terms of the number of times that it's divisible by a given prime number. And so that's what I was talking about in the video. If you write out all of the prime factorizations of each of the positive integers and then count the number of 2's, or if you look at the exponent, say the exponent of 2 in the prime factorization of the number, you start to see some weird patterns. For example, if you just look at the sequence of exponents of 2 in every prime factorization, you get the following sequence of integers: 0, 1, 0, 2, 0, 1, 0, 3, 0, 1, 0, 2, 0, 1, 0, 4, 0, 1, 0, 2, 0, 1, 0, 3, 0, 1, 0, 2, 0, 1, 0, 5, 0, 1, 0, 2. And it's like, it's got a little pattern going on in it, but then you get these random 5s out of nowhere. Like, what's happening? And so I dug around on with 3's. If the 3-adic valuations of n, that is the largest power of 3 that divides any given integer, are 001, 001, 002, 001, 001, 003, 00, no, 2, no, wait, yeah, 3, 001, 001, 002, 001, 001, 004. And then 5, it's 0001, 0001, 0001, 0001, 0002. Like it's weird. It would be helpful. Do they have whiteboards in Zoom?
Yes, let me
What?
figure that out. Let's go here.
And then we'll see if you guys can tell me what the pattern is. No cheating by looking at the OEIS.
Do you see this?
I see
And
white.
yes, if you mouse over the top, you can click a button and then click annotate. Similar. Mouse over the top of your screen. There should be a little bar that will pop up. You can click something, then click annotate.
No, it's not giving me the option on this end. Alas.
Perhaps it would be easier here. If you can probably do this. If you click share screen.
All right.
And then click blank
whiteboard.
screen. Like whiteboard? Yeah.
Okay. Share. Ooh. All right, are you guys all seeing this whiteboard thing here? If I write on it? Wow. This is so much more pleasant than the whiteboard in Adobe Connect. This is great. So here's the deal. Tell me if you guys can see the pattern in this. Will you go away, please? Clear. Delete. It won't let me delete the thing. Now will you let me delete? Select that. But we did. Noise. So these, my friends, the two adic valuations of n, where n are the positive integers, the natural numbers excluding 0. That basically just means what's the largest power of 2 that evenly divides. And here's the sequence. 0, 1, 0, 2, 0, 1, 0, 3, 0, 1, 0, 2, 0. No, we want to keep it all on a line because it's prettier that way. Now I lost my place. 0, 1, 0, 2, 0, 1, 0, 3, 0, 1, 0, 2, 0, 1, 0, 4, 0, 1, 0. Do you guys, anybody have any ideas about what the pattern might be here? I don't see text chat anymore. It has disappeared and gone away.
Anyone sees a pattern, feel free to just unmute yourself and say it. Oh, that might be a bad idea.
Here are the 3 adic valuations of n.
You can raise your hand if you go to the participants button on the bottom of the screen. So if you think you see the pattern, feel free to raise your hand. And if you don't see how to raise your hand, put a message in chat. And if you don't see chat, I'm afraid I can't help. Chat is also on the bottom of the screen, but if you do that, you should be able to see the participants button from where you should be able to raise your hand. So raise your hand if you think you see the pattern.
So there's the 3 adic valuations of n, the highest power of 3 that evenly divides each number. So what you're thinking of is each of these numbers in the sequence being paired with one of the counting numbers, 1, 2, 3, 4. So in the 2 adic valuations of n, 1 has a 0, 2 has a 1, 3 has a 0, 4 has a 2, etc. Here's the 5 adic valuations of n. There is an algorithm for this, or else I wouldn't be able to remember it. Whoa. This is riveting.
If no one can see a pattern, again, if you do, raise your hand, put something in chat. If you can't figure out how to do either, I guess you can just unmute yourself, but I'll probably regret saying that, but that's fine. So do one of those things if you see a pattern. Otherwise, okay.
Anybody yet? Here's the 7 attic valuations.
Are you able to see chat?
I am not now.
Okay, so Ellie said every time there's a new power of n, it increases by 1.
Yes, right. And that makes sense, right? You would have in the 2 attic valuations of n, the first number is 1. It has no 2's in its prime factorization. The second number is 2. It has 1, 2 in its prime factorization. That 2 there, 0, 1, 0, 2, that's 4 because it's 4 squared. The 3 in the 2 attic valuations of n, that's 2 to the 3rd, which is 8. So that's the 8th number. 2 to the 4th is way over there, which is whatever that is.
Someone wants to know if you can more explicitly define what you mean by a pattern, like an explicit formula.
Either a formula or an algorithm for producing it.
Yeah, so it can either be like a formula or a recursive thing, something like that.
Yeah, and my claim is going to be that these are fractal sequences. These are integer sequences that contain themselves. And the easiest way to get a fractal sequence is if you have some recursion going on. So the algorithm for, there are ways of producing these sequences that don't involve recursion. There's a generating function for them. If you search around on OEIS, you'll find a generating function. You'll also find a kind of fancy function that involves lots of flooring and sealing that would get you these, but I think the easiest way to do it is recursive.
And if you want to give, so Ethan said for 2, it is that you start with 0, then copy the previous elements of the sequence, adding 1 to the final element, then repeat.
That's it. That is the sequence. So the algorithm for these is you always start with 1, 0, and then you duplicate that 0 p number of times. So if you have the 2 attic valuations of n, p equals 2, and so you start with 1, 0, and then you repeat it. I don't know where to put the chat pod now. You repeated that number of times, and then you increment the final number in the sequence. With 3, you start off with 1, 0, and you repeat that p number of times, which is 3, so you end up with 3 zeros. So you end up with the following kind of step-by-step algorithm, and using this, you can do a number of things. The 2 that I am most interested in the moment are that using this algorithm, you can calculate all of the prime factors, the prime factorizations of every integer without doing any calculation. No actual calculation is necessary. And also you're able to find all the primes without doing any calculation because it ultimately amounts to a kind of sieve of Eratosthenes. So here's how the algorithm works. If I want to do, say, the 3 attic valuations, so I want to figure out what is the power of 3 the highest power of 3 that evenly divides 3 attic valuations of n. And what I do is I start off with 1, 0, and this is the way it always starts. And then I duplicate that till I have 3 of them. And then I increase the last one by 1. And then I duplicate that till I have 3 of them. And then I increase the last one by 1. And then I duplicate that till there are 3 of them. And then I increment the last one by 1. And then I duplicate that till there are 3 of them. And if you have any experience with the ways in which fractals are often generated, there is one method of generating fractals is called the Linden, is through Linden-Meyer systems. You will see that a lot of the most famous fractals, like the dragon curve, have very specific, these recursive ways of defining what the sequence is. It took me forever, though, to actually figure out that that was the general pattern. It works for any prime number. So if I wanted to do the 5 attic valuations of n, I would start off with a single 0 and then duplicate that 5 times. increment the final number, and then duplicate that 5 times, increment the final number, duplicate that 5 times, and so on. It works for any of the primes, and what that effectively means is that you can go and, if it will let me delete stuff, but we did. What you can do is, if you're ever stuck, you don't have a calculator on hand, and somebody asks you, give me all the prime numbers and all the prime factorizations of every positive integer, and I say, all right, give me a second. All right, so here are the positive integers. I say, be patient with me, because the person who's holding a gun to your head saying, calculate all the primes and prime factorizations. I'm like, geez, chill out, dude. And what you do is all you have to know is...
I think this might be a good place to pause. I want to see if anyone can know how to do this based on what we have so far. I think it might be a good opportunity for that. So does anyone know how we might find the prime factorization of each integer based on what we've done so far? Sorry to interrupt. I just think it's...
Oh, that's a great idea.
So
make it prettier.
Okay. So what we have so far, right, is that for each integer, yes. Okay, so someone said just write like 288, 388, etc. And those are the exponents.
Good.
Yes. So Easton said that, and then Ellie said, well, you could just use the algorithm already described up to the highest prime here, 13, and then just multiply it. So yeah, we both essentially said that.
Etc. And then as you go along, what you do is you ask yourself, I don't need to know any of the primes ahead of time. All I have to do is know how to count. And I have to know that 2 is the first prime. That's the only things I have to know is how to count and that 2 is the first prime. Once I've written out the p-adic valuations of 2, so the 2-adic valuations, sorry, then I say, what's the next number? The next number is 3. And what I do is I go over till I get to the 3 column, and I look above where I currently am. So I look at the 3 column, and I ask, is there any numbers in there that are larger than 0? If not, I have a new prime number, and I add a 1 there. And then I can fill out its pattern, etc. And then I move on to the next number. 2 next comes up as 4. So what I would do is I would go over to the 4th column and ask, are there any numbers in this column larger than 2 below the top row, right? The top row, these guys are just keeping the place of the integers. And there's already a 2 in this column, so I forget all about 4. I just skip it. And I go on to the next number, which is 5. And I go over to its column, and I look at it, and I see, do I have all zeros? I do. So I've got a new prime number there. That means I've got 0, 0, 0, 1. And then I can duplicate that. And it would end up duplicating 5 times, etc. And then I look at 6. And I say, all right, is 6 prime or isn't it? I go over to the 6th column. Oh, dang, it's got 2 1s in it. And you will note that that should be right? The prime factorization of 6 should be 2 to the 1 plus 3 times 3 to the 1, right? So you've got, it already tells us, I can just read off the prime factorization of 6 right there. And since 6 already has a prime factorization, it's already got numbers, I skip it and I go on to 7. And so I go over and check 7's column. There's nothing in 7's column, it's all zeros, so I stick a 1 there, and then I duplicate. This is, if you think about it, with the sieve of Eratosthenes, where you cross out, you start with 2, and then you cross off all the multiples of 2, and then you go to 3, and you cross off all the multiples of 3, and then you go, and then 4 is already crossed off because it was a multiple of 2, and then you go to 5, and you cross off all the multiples of 5. That's basically what you're doing here. It's just that what I find fascinating about this entire thing is that not once do you actually have to do a calculation. If you know how to count, and you know how to check rows and columns and how to duplicate things, you can end up figuring out just by reading down a row that, for instance, the prime factorization of 10 is 2 to the 1 times 5 to the 1. The prime factorization of 12 is 2 to the 2 times 3 to the 1. My question now is, does that make sense to you? Because I'm not able to actually like bold these things and underline them. So yeah, it is like an abacus, isn't it? Yeah, interesting. So this is actually how I got started. I just had an Excel spreadsheet open and I was listing things off. And I decided that I wasn't going to care about leaving out the primes. Typically, I don't know if you guys have had math classes before, but when you're taught how to do prime factorizations, you're always taught to leave out the primes that have an exponent of 0 effectively, right? So you would write the prime factorization of 10, you would write as 2 to the 1 times 5 to the 1, right? So you have 2 to the 1 times 5 to the 1. But because I was doing this in Excel, I always had this 3 sitting there in between them. And so I decided to not worry about that. And the reason why I don't have to worry about it is, you guys know what something to the power of 0 is? What anything to the power of 0 is? Yeah, that's the weirdest thing in the world. Like, who decided that? But I'm glad that they did. So there's no problem with sticking in that 3 to the 0 in there. It can mess up some of the technical definitions about prime factorizations. There's a requirement that every prime factorization be unique, that each integer have only one prime factorization, and if you allow all these prime factor to the power of 0, then you can end up having 15 different ways of writing the prime factorization of a number. But I'm not a mathematician, so I don't care. Like, I can come in and mess up the whole mathematician's china shop and then go away squealing with laughter. And it's not going to affect me because I'm a philosopher. I just do philosophy of math. I don't actually do math. But once I had written it out with all these zeros in there, I had to then figure out the pattern. And I was like, there's some pattern here, but I can't figure it out. And it was after digging around on the OEIS that I finally figured it out. Now, if you would, I'm going to put a link in text chat. And let's see if it works. So I've just put a link in text chat. The link is, I will also put it here on the board. You can take a look at the app that I used in order to generate all of these things. So please do that. I'm not going to do it here on my end, but please go to that link and play around with it for a little bit. After seeing what I thought were patterns in the zeros and ones, I was like, could I make this visual? And I realized that I had been learning how to use the Unity game engine. And that Unity allows you to do whatever programming you want and has an entire rendering system built into it. With previous iterations, I had used Java FX, and that was so much harder to work with. Good point, Ethan. Yeah. Oh, I didn't put it in the link in the text chat. I put it in a private message to Quinn. That's embarrassing. I would recommend, is everybody able to access the app? Is anybody having problems with it? I don't know how much my server can handle with people trying to run heavy JavaScript, but I hope it works. I have spent many happy hours hunting for fractals in this program. For instance, if you ask that program to articulate the line using powers of 2, and then you set the degree to 90 or to 1 times pi over 2, you'll see the Levy C curve, the Levy dragon fractal.
Do you want a screen share of this? Like,
I mean, I could do that.
do you think that would help what you're explaining? Or?
Sure. All right, let's close that. And I will share my screen. I don't want to show you my calendar. No. How about I'll show you YouTube. Oh. Number line. Made with Unity. Unity is awesome because it is free. Like all the best things in life. All right, so for instance, if it's already set to 2, if I set it to 90 degrees down here in the lower left and hit enter, I can zoom out with O, I can zoom in with I for in, O for out. You can move around. And then I would suggest that you add extra iterations. So currently it is drawing the number line from 1 to 2 to the 5th minus 1. I suggest you go up to something like 2 to the 10th minus 1. You can zoom out some more, or you can just lower the spacing of the line. So currently it's set to space out each by 8. If you do it to 4, it'll shrink it down. You guys may recognize this. I don't know if you do. That's the Levy C curve, or the Levy dragon. If you set it instead to 120, you get the Levy diamond fractal. And one of the interesting things you will find is that this is not the Levy diamond that you will normally see. If you were to Google Levy diamond right now, you wouldn't see that. What you would instead see is this. I'll put it back to 120. And let's lower the spacing down to 2. Gosh darn it, it's doing that thing where it erases. No, do it to 11. There you go. This is what you would see typically if you were looking at the Levy diamond. And one of the things that puzzles me, and I hope maybe one of you guys can figure it out, is why is it that some of the fractals, when you generate them with this algorithm, go through cycles? So this one has a cycle of period 2. So at 2 to the 10, it looks like this. At 2 to the 11, it looks like this. At 2 to the 12, it's going to go back to the other version where it's got this kind of duplicated sign. Then 2 to the 13, it'll go back to being normal. With these, I would suggest that you switch the display option to line. When you do that, it gets rid of all the spheres that it's using to represent the individual points on the number line, and that saves a whole heck of a lot of memory. And that will allow you to do a lot more. And I have had an absolute blast going through this and finding new fractals. For example, if you change this, let's set this back to 5 to stay safe. And we set this to say, do it based on powers of 10. Here's what you get with powers of 10 at 120 degrees. Watch this. Any Zelda fans in the house? Yeah, the Triforce of Power there. You might be able to predict what 7 to the 8th will give us. It's going to take it a while to do the calculations. Let's actually shrink it down to a spacing of 1. Let's zoom out a little bit. I think we would all agree that this is a fractal. I think. I mean, I'm not a mathematician, just a philosopher of math. But like if I cycle back through these, it looks like that image consists of copies of itself, which consist of copies of itself, which consist of copies of itself. Or take a look at 7 to the 144. You see that? You say, what's going on here? Well, 7 to the 2, it's a star. And now what I've got is a star made of stars. And now here's a star made of stars made of stars. There's one side of a star. It does this sometimes. Why does it do this? No other fractal generating algorithm that I have found will give you these cycles. It's always the same. But with some of these fractals, not all of them, the Lebesgue curve doesn't do it, but this one does. It's a star made of star made of stars. You can make the line thicker if you would like, so you can thicken it up so that you can actually see what's going on, etc. And then if you get bored of just hunting for fractals, you see in the bottom right-hand corner of the screen, and can I, yeah, you can hit animate, and it will animate it for you, although it will go very slowly if you have a very long number line. So let's switch it to 3 to the 7. It'll be much happier with that. We'll animate it, and you can space it out while it's going. And another thing that I would suggest that you do is try to have it display in the display thing, have it display a trace. And if you zoom in on this, you'll see that it's tracing out what effectively is, what we're doing here is a kind of Fourier transform. Let me reduce it even further so you can see what's going on. Let's go to 2 to the 5. And let's start at 0. Have you guys ever seen a Fourier analysis of like orbiting planets? You've ever taken a class on like ancient astronomy where they believe that planets orbited on epicycles on epicycles on epicycles, and they weren't entirely insane because the ultimate paths traced out by those might have actually been the real orbits. So you can do that in this and just see how the 2-adic valuations go. And if you want to see multiple powers of 2 tracing out their curves, you can turn on display traces instead of display trace, and that will get you multiple curves at the same time. One of the interesting things you find out when you do this is that you end up with each power of 2, the point that represents a power of 2, or rather a power of 2 minus 1, crosses through 1 over and over again. It's like this attractor that it keeps coming back to. And again, I don't know why it does that. So I have been, after playing with all of this, I have been setting up a catalog of all of the patterns and fractals and non-fractal things. If you noticed in the video, not all of the things that are formed are fractal. Every single one of them is being generated by a fractal sequence, but they're not all fractals, and I don't know why that happens either. So I come out of this both delighted and very puzzled, and I will have a handout for you that Quinn has that has a lot more information on some of the weird things that you can do with this, and also a series of research questions, which if you can answer, you will be the first person in history to derive a simple formula for predicting where the next prime is. And you'll be famous, but I have been unable to answer them myself. But I think I have been talking for long enough, so perhaps I should open the floor to questions or comments.
Yeah, so first of all, to find that handout one sec, I think it should be at virtualmathcircle.org/meetings. And then if you scroll down, you should be able to see the problem sets. And under week 1, if you click download, it should at least theoretically download. And if that doesn't work, well, I hope it works. So, and then so if you can try to, there's the link. Oh, you have to see some component. Hopefully, it should be linked under the week 1 problem set. If it doesn't, let me know. And if anyone has any questions, raise your hand, put it in the chat, do something, let us know if you have questions. And then after questions, we will start looking at it. It's not downloading. Okay, let me try to change that. In the meanwhile, if you have any questions about what Dr. Tillman has just presented, please do ask them.
I think what I have found here is that the number line, the natural numbers, are generated by an intersection of an infinite number of fractals. If you think about it, if every single one of the p-adic valuations of n is itself a fractal sequence, and it's those sequences that determine the prime factorizations of the integers. And it takes an infinite number of fractals working together in order to generate a very simple 1, 2, 3, 4, 5, 6, 7 sequence. And if you can crack the code, if there is one, you would be able to derive a formula, it seems to me, that would get you be able to predict where the next prime was going to show up. Unfortunately, most of these, one of the things you learn in computer science, and I was a computer science major, is that you always have a time-space trade-off. And in order to be able to do all this fancy stuff, you end up taking up a lot of space, you know, all these infinitely long sequences. And so it's unlikely that you'll be able to find a formula that is any more efficient than the formulas that have already been found. But there's some interesting stuff going on.
So I'm currently working on getting it up. My computer is probably slower than yours, so that may take a little bit of time.
All right, then in the meantime, let me do one other thing. So I'm going to stop this somehow.
If you want to also, if you have the questions, if you want to just put one of them up at any time, you and Fire, we could start discussing it that way.
All right. All right, so here's a question for you. Imagine, actually, let me write it on I'll put to a whiteboard for this. So we have established that we can summarize the prime factorizations of numbers by just listing out the powers of the primes that go into them. So for instance, the number 6, we could represent with this sequence. Sorry, 1, 1. Right? Because 6 is 2 to the 1 times 3 to the 1. 10 is equal to 1, 0, 1, because it's 2 to the 1 times 3 to the 0 times 5 to the 1. 15 is, what is 15? 2 to the 0 times 3 to the...
So my computer's not happy right now, so I'll put it up after this meeting. For now,
it's brilliant. And just you wait.
Oh, yes, so it is exciting. But if you want, you can either put the questions on the whiteboard or one of us can screen share, which you prefer to do.
So here's my first question. If you translate the numbers into their prime factor powers, and you represent them that way, how would multiplying 6 times 10? Yeah, it looks like binary, doesn't it? It looks like binary. Of course, you're going to get numbers like 2 and 3 and whatnot.
You should all know that 10, 10 is 10 in binary. So next time it's 10, 10 on the clock, say it's 10, 10. That's 10 in binary. That was important.
Exactly, Easton. Yeah, that's exactly right. Multiplication becomes addition. If you write 6 out, then 6 is 1, 1. So it's 2 to the 1 times 3 to the 1. And 10 is 2 to the 1 times 0 to the 1 times, sorry, 2 to the 1 times 3 to the 0 times 5 to the 1. And if you add those two up, you get 2, 1, and 1. So that's 2 to the 2 times 3 to the 1 times 5 to the 1. And that should get you 60. Does it? I hope it does. 2 to the 2 is 4. Okay, thank God. All right, I was panicking there for a second. Furthermore, division becomes subtraction. If I wanted to divide, for example, 30 by 15, I could write out the, so, whatever. So the general, I call that the prime power place system instead of a place value system, which is what we normally use, and we normally use powers of 10, but you're writing the coefficients of the powers of 10, right? It's in the handout, which you will get eventually. I call this the prime power place system. And in this system, when you add two numbers together, you're actually multiplying them. When you subtract one number from another, you're dividing it. So 30, what's 30? It's the prime factorization of 30. It's 2 times 15, which is 2 to the 1. Oh, it's 1 and 1 and 1. Nice. And imagine that I wanted to divide that by 15. So I divide that by 15, and 15 is gosh darn it, having to think backwards, because numbers, you always flip them, right? So that's 5 to the 1 times 3 to the 1 times 2 to the 0. And then if you subtract those two from each other, you end up with 0, 0, and 1, which is 2. That's 2 to the 1. So when you add numbers together, you're multiplying them. When you subtract numbers in this system, you're dividing them. Guess what happens if you multiply? So for example, if I have 6 is easy, 1 and 1. And let's say I wanted to find out what 6 squared was. Yeah, I know, you have to decide which order, which direction you want to write it in, Easton. That's a great point. Does it ever weird you out that when we write numbers like numerals, the larger numbers are to the left, everything you own in the box to the left, but when you write out numbers on a number line, the larger numbers are to the right? I don't know why we do it that way, but so long as you're consistent, it'll work out. The order doesn't matter if you're consistent in the way you're ordering things. But if I wanted to figure out what 6 squared was, then I could write 6 as 1, 1, because it's 2 to the 1 times 3 to the 1. And then I would just have to multiply that by 2. So if I multiplied that by 2, I would end up with 2, 2, which is 2 squared times 3 squared. Does that get me 36? 2 squared times 3 squared? It's 4 times 9, it gets me 36, right? Yeah? So multiplication is addition. Exponentiation is multiplication. Same thing for taking roots. It's division. Yeah, I guess so, Ethan. Yeah. 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 Who knows? Anyway, with the Cartesian coordinate plane, at least, it's reading from left to right, which is how we normally do it in Indo-European language. Well, in modern European languages, maybe not all Indo-European languages. Taking roots is division. So if I wanted to figure out, for instance, if I've got 36, so 36 is equal to 2, and I wanted to figure out what the square root of that was, I would just take 2, 2 and divide it by 2. So I divide that by 2 and I'd get back to 1, 1, and then I would have the square root. And you can do the cube roots of stuff, and then you can see immediately which numbers are square rootable and which are cube rootable, so which are cubes, which are squares, just because of the numbers in the thing. There is an entire branch, my friends. There's an entire branch of mathematics that deals with all these p-adic valuations of n. You can look it up. It's on Wikipedia. I have no clue. If Dr. Galula were here, he would be able to explain all these p-adic orders and p-adic norms and stuff. And I strongly suggest that you walk around saying p-adic over and over again. It makes you sound like you're not crazy. Anyway, so this is something that I just realized 2 days ago. I was trying to go to sleep at night, and I asked myself, what would multiplication look like? Right. Good question, Easton. I don't know. I haven't tried that yet. I would love to find out. Here's my main problem. So here's a problem for you. When we add two numbers together, we're actually multiplying them. How do you then add two prime factorizations? If I give you two prime factorizations, say 6, which is 2 to the 1, times 3 to the 1, and I give you the prime factorization of 12, which is 2 to the 2, times 3 to the 1. Would you be able to predict that the outcome of that, of adding those two together, 6 plus 12 equals 18, what's the prime factorization of that? Yeah, I leave all this stuff up to you guys because I've about hit the limit of my mathematical abilities. All I can do is be like Hilbert, when Hilbert got up in front of everybody and said, here are 15,000 open problems, and then if you solve any of these, you get $1 million from the whatever. What's the prize? What's the people, there's still some open questions in mathematics that you'll get $1 million for. 2 to the 1 times 3 to the 2, thank you. So if I were to write this out in my, and just using the exponents, that would be 1, 1 added to 2, 1 equals 1, 2. If you can figure out how this works, like what's lower than addition? Yeah, the millennium problems, I think, are the ones I'm thinking about. Because when you try to add two numbers in this way of representing them, you end up multiplying them. So multiplication is addition, exponentiation is multiplication. What's simpler than adding? That, if you look, once you guys get the problems, you will see that a lot of these are not problems, they're open questions for further research. And if you can solve them, yeah, doing nothing, right? It's like, and so clearly if you do nothing, then it kind of is that way, right? Because what's 1 in this system? It's 0, 0, 0, 0, 0, 0, 0, 0. And so if I'm adding 1 to something, then I'm just adding a bunch of zeros to it, and somehow that, like, I know how to count and how to add and how to do all that stuff in binary. It makes a lot of sense in binary, but because I'm doing these, each column is a prime number, and you're doing these multiplications and powers, it's insane. So I've got some stuff like that in the things. Another thing you have to keep in mind when you're doing this stuff is that you have to keep the numbers separated, because eventually you'll get to like whatever 2 to the 10th is. Does anybody have a calculator and tell me what 2 to the 10th is? And when you do that, you're going to end up with, really, it's only 1024? Oh, okay. Well, it's less interesting than I thought, but thank you. It's not your fault that it's smaller than I was expecting it to be. I've been thinking about teraflops recently because of the PlayStation 5 and Xbox Series X arguments about who's got more teraflops. And so anyway, because once you get to 2-digit powers, you end up having to cram 2 letters into one of these, two numerals into one of these spots. I have tried to avoid just running things together, but it is super tempting just to put them all together. But anyway, I have projects going on with related to this. If you go to micatillman.com/numberline, not numberline app, but just numberline, you will find a link to my current catalog of all of the shapes and fractals that I have found in the 2-adic valuations of n. I'm working on the catalog of all the 3s, but if you find other ones by playing around with the numberline app, I would love to add them in. You will note that on the, if you go to micatillman.com/numberline and then click on the 2-adic valuations of n, you will see, well, I guess I should just do it instead of talking about it. Share my screen, share my screen. Yeah, share that. Tillman.com/numberline. No, not numberline app, numberline. Numberline, don't autofill. You'll find links to the full 7-hour animation, which took me days to do. So you better like it. The music is also randomly generated and it's a fractal. There's 7 hours of fractal music that's based on the sequence. And if you click on the 2 attic valuations of in, you will notice these are some of the images I found. Do you guys recognize any of these shapes? Like I've already said that this one here in the middle, that's the Levy C-curve. The one on the bottom right is the Levy diamond, at least one version of it. But do you recognize these squigglies? You guys ever seen the cock snowflake, which is a hilarious name for things? What's botto? Is that a word? Oh, I wish it was a word. It's a good word. I'm going to use it. I'm going to name one of these the botto. The top left one, that's the botto now. Noise. Anyway, if you look up, again, I'm teaching you all kinds of fun words today. P-attic. That has happened to me a million times. If you scroll down, you will see a number of different things and take a look. It's in a book, A Reading Rainbow. This is a version, I'm sure of it, of the cock snowflake, the Coke snowflake, with an angle set to a different angle. Here's another version that's similar. And then I should probably let you guys go, but let me just show you one thing. Where is it? I love this one. This is a fractal that has a period of 11. It has 11 different forms that it cycles through. No one in history has ever seen this fractal before me. Take that, people who actually know how to do math. I made a thing in Unity that makes pretty pictures, and I saw one before you did. If you look at these ones here, this is at 144 degrees in base 2. This looks a whole heck of a lot to me like one of the Von Koch snowflake things, but with the I spelled snowflake right. That is right. That is the correct way of spelling snowflake. I'll have you know. And so it's weird. It's weird to me that the Levy C-curve might be related to the Koch snowflake, even though nobody's talked about that before that I have seen. So anyway, I have. That's true. No, yes. I need to remain humble. I need to, in the words of the philosopher Kendrick Lamar, I need to sit down, be humble. So I will be quiet now. I assume that we're probably coming up to the end of things.
All right, so thank you everyone for coming today. We will have another lecture next week around the same time. I can't tell you, we probably will have another lecture next week around the same time. I'm talking to several people. We'll definitely have one 2 weeks from now, probably one next week. I can't tell you the topic yet, but I will figure it out. Email everyone who signed up for this, everyone who RSVP'd to this talk. I will email you about the next topic when I get that. But it'll be same room, probably the same time, but no guarantee. And next week. So with that, there will be a recording of this on the website as well. I will put up the problem set, I promise. And Dr. Tillman, if you have any closing remarks.
This is just, it's been a lot of fun for me. And again, thank you guys. Yeah, it just has the unsolved problems, Easton. Yeah, so I hope that you solve them and then win one of those Millennium Prizes. Thanks, everybody.
Thank you for coming. And I hope to see you all next week.